atomic spectra and Bohr model of atom, emission of discrete spectral lines from hydrogen atom, emission of discrete spectral lines from hydrogen atom. Yeah, 2 times that. Same thing. Okay. Bohr model of hydrogen atom, experimental support of Bohr's model, Frank Hertz experiment, Sommerfeld's generalization of quantum rules, space quantization and Stern Gerlach experiment, limitations of Bohr Sommerfeld model, matter waves, de Broglie's hypothesis, experimental verification of matter waves. In the preceding module, we studied the quantum nature of electromagnetic radiation at a microscopic level, and being aware of the fact that the phenomena of interference, diffraction, and polarization of light can be successfully explained by the wave properties, we reached to an important conclusion about the dual nature of electromagnetic radiation. It has the ability to manifest itself either as waves or as photons. Parallel to these developments, side by side were equally startling discoveries regarding the atomic structure of matter. In this module, we shall review these attempts and show how these laid the foundations of quantum mechanics. In particular, towards the last section, we introduce de Broglie's hypothesis of a dual wave particle character of matter at the atomic level. This hypothesis was experimentally verified later by Davison and Germer, showing that material particles like electrons possess wave-like properties exhibiting interference and diffraction. Atomic spectra and Bohr model of atom. Emission of discrete spectral lines from hydrogen atom. By the end of 19th century, a lot of experimental data on the radiation spectrum of atoms was accumulated. In 1885, a major discovery was made by Balmer, who studied the spectrum of hydrogen atom and found that in the visible and near ultraviolet regions, the spectrum consists of a series of lines denoted by H alpha, H beta, H gamma, now called the Balmer series. These lines come closer together as the wavelength decreases till they reach a limit at a wavelength lambda is equal to 3646 angstrom. In 1889, J.R. Rydberg found that the apparent regularity in the lines of Balmer series could be expressed in terms of the wave number lambda dash is equal to 1 by lambda. According to Rydberg, Balmer lines are given by this equation. N is equal to 345 like that. And RH is the constant for atomic hydrogen. Its value determined from spectroscopic measurements is RH is equal to 1.097 into 10 raised to 7 m inverse. RH is the constant for atomic hydrogen. Its value determined from spectroscopic measurements is RH is equal to 1.097 x 10 raised to 7 meter inverse. A Balmer series of atomic hydrogen. As shown in this figure, this spectrum consists of a series of lines denoted by H alpha, H beta, H gamma, lying in the visible and near ultraviolet region. Other series of spectra for hydrogen were subsequently discovered. They are known as Lyman, Paschen, Brackett, and Hunt series, known after their discoveries. It can be noticed that the formula given by Rydberg for the Balmer series could be easily generalized to the series as well by writing the formula in a general form like lambda wave number is equal to RH 1 by n A square minus 1 by n b square. A particular series of lines is obtained by setting NA to be a fixed integer and letting NB take the values NA plus 1, NA plus 2. The series are then given different names. For instance, the series with NA is equal to 1 is known as the Lyman series and it lies in the ultraviolet part, where NA is equal to 2 is the Balmer series, and the series with NA is equal to 3, 4 and 5 are called the Paschen, Brackett and Hunt series. These emission lines are shown in this next figure, I guess. Yeah, emission lines of hydrogen spectrum. Lyman, Balmer, Paschen, Hunt. The Rutherford model of the atom. Soon after the discovery of the electrons by J. Thomson in 1897, the first outlines of the atomic structure of matter became known. When an atom was supposed to consist of a number negatively charged electrons plus a positively charged residue. However, the picture of the atom became clearer when in 1911 Rutherford's analysis of experimental data on the scattering of alpha particles by thin foils of different elements, carried out in 1908 by Grigor and Marsden, arrived at the conclusion that all the positive charge and almost all the mass of the atom is concentrated in a positively charged nucleus of dimensions compared with the dimensions of the atom as a whole. This immediately suggested a planetary model of the atom in its structure, very much similar to that of molar system, with electrons orbiting around the nucleus, like planets orbiting around the sun. The electrostatic force of attraction between each electron and the nucleus hold the nucleus together. It was soon realized that this picture of the atom presents several difficulties from the point of view of classical theory. In the first place, due to the orbital motion, the electrons would get accelerated and emit radiation continuously. Subsequently, the electrons, thus losing energy, would spiral inwardly and eventually collapse into the nucleus. This result is contrary to experiment, since the atom is known to be very much stable. Moreover, the frequency of the emitted radiation, which coincides with that of the orbital motion, should continually increase, thereby producing a continuous spectrum instead of the observed discrete spectral lines. It is thus clear that electromagnetic theory, despite its success in explaining large-scale phenomena, could not be applied to the process at the atomic scale. Bohr model of hydrogen atom. In 1913, the Danish physicist Niels Bohr realized that to overcome the situation discussed above, a fairly radical departure from the established principles of classical mechanics and electromagnetism would be required to understand the structure of the atom and the atomic spectra. Accepting the Rutherford model of the atom, he proposed the following basic postulates to explain the dynamical behavior of atoms. Bohr's postulate, according to his first postulate, the system of electrons and nucleus constituting the atom cannot exist in any arbitrary state of motion allowed by classical theory. It can exist only in certain special orbital states. Each possible state has discrete value of the total energy. The electron in an atom could revolve in certain stable orbits without the emission of radiant energy. These are called the stationary states of the atom. The electron in the atom revolves around the nucleus only in those orbits for which the angular momentum is an integral multiple of h by 2 pi. In other words, the angular momentum L of the orbital electron is quantized. L is equal to nh by 2 pi. This is the hypothesis of quantization of angular momentum. Emission of absorption of radiation takes place when the electron makes a quantum jump from one stationary state to another. When the electron jumps from a higher energy state EI to lower energy state EF, initial to final, I guess. So Bohr, following Planck, suggested that the difference in the energy is radiated as a photon of energy nu, given by the relation EI minus EF is equal to h nu. As a consequence of these postulates and using classical method, Bohr obtained the expression for the energies of allowed stationary states in the following way: assuming the nucleus to be very heavy compared to the mass of the electron and is therefore at rest, the electrostatic force of attraction between the proton and the electron is equated with the centripetal force, like E square by 4 pi epsilon 0 r square is equal to m nu square by r, where epsilon 0 is the permittivity of free space. Using Bohr's second postulate, the magnitude of the orbital angular momentum of the electron is quantized, giving L is equal to mvr is equal to nh by 2 pi. N is equal to 1 to 3, like that. From these equations, we get the expressions of the allowed values E and R. Bohr has established that the frequencies of spectral lines of any atom can be expressed in terms of the difference between spectral terms or stationary state energies characteristic of each atom. In fact, a similar relation known as Rydberg-Ritz combination principle was already observed empirically. The striking agreement of the Bohr with the observed spiral lines of hydrogen-like atoms clearly showed that Bohr's postulates, though ad hoc in nature, are basically sound. Experimental support of Bohr's model. Frank Hertz's experiment. The existence of such discrete energy levels was confirmed by the Frank Hertz experiment on the scattering of a beam of monoenergetic electrons by atoms. They noticed that as long as the energy of the electron beam was below a certain minimum value, the scattering was purely elastic. If, however, incident energy exceeds this minimum value, it can still accept only the exact amount, where E0, E1, E2, where E0, E1, E2 refer respectively to the energies of the ground, first excited and second excited states, and the atom can go from the ground state to the first and the second excited states by absorbing these differences of energies. When the incident energy is increased sufficiently, inelastic scattering absorbing the discrete amounts of energy are found to take place. Sommerfeld's generalization of quantum rules. Besides the remarkable success achieved in explaining the atomic spectrum, it was felt that the quantization condition of the orbital angular momentum employed in their derivation was valid only in the case of circular orbits and could not be used in more complicated cases. Soon it was noticed that above condition is in fact a special case of condition. Here, Q refers to some generalized coordinate and P is the corresponding canonically conjugate momentum. Considering P as a function of the position Q of the particle on the trajectory, the integral is to be taken over one period. For example, in the case of an electron revolving around the hydrogen nucleus in the plane elliptic orbit, with the nucleus at one focus, the single Bohr condition is replaced by the two conditions. The quantization of the elliptical orbits of the hydrogen atom by Sommerfeld is worth mentioning because it gives for the first time the first example of two general properties which persist in quantum mechanics. First, the property of degeneracy of energy levels of systems. Sommerfeld noticed that the quantized elliptical orbits in a given plane are characterized by two quantum numbers n r and k representing the radial and angular parts of the orbital motion. He observed, however, that the energies of the quantum states depend only on the sum n is equal to nr plus k of these quantum numbers. Thus, for a given value of the principal quantum number n, there are different states, elliptical orbits of different eccentricities corresponding to k is equal to 1 to lead to n. All of these have the same energy n. For example, for n is equal to 2, we can have k is equal to 1, 2, giving two-fold degeneracy, and for n is equal to 3, there is a three-fold degeneracy. Such a system with energy level En, when the quantum orbits in one plane are considered, is said to be an n-fold degenerate. It has now been understood that this degeneracy in the case of hydrogen atom essentially arises due to the dynamical nature 1 by r dependence of the electrostatic potential. The second general property which is built in the treatment given by Sommerfeld is the removal of degeneracy when the symmetry is broken. This is due to the fact that the variation of the speed of electron in hydrogen atom as it moves along an elliptical orbit includes corresponding changes in its mass given by the theory of relativity. This mass variation, Sommerfeld showed, gives rise to a slow precession of the orbit in its own plane. It causes the change of orientation of the ellipse at a steady state. As a result, the energy associated with each orbit is changed by a small amount depending on the quantum number k. As a consequence of this, the nth Bohr level splits into n closely spaced levels, thereby removing the degeneracy. The spectral lines split in this way give rise to what is called a fine structure. For in the above, while discussing the degeneracy of the nth Bohr model level, we considered the orbits in one plane only. In other words, we considered only the orbits with respect to a particular direction for the angular momentum vector, which is normal to the plane of the orbit. In fact, there is further degeneracy arising from the possibility of various orientations for the angular momentum vector with respect to a fixed axis. This axis may refers to directions of some externally applied field, say for instance the magnetic field. Specifically, the component of the angular momentum parallel to its axis has to be m eta, quantum number m taking integer values only. For orbital angular momentum of magnitude 1, the values which m can take are limited. M is equal to +1, +1, -1, +1, like that. This is called space quantization. This concept of space quantization was demonstrated in an experiment by Stern and Gerlach. They made use of the fact that an atom having non-zero orbital angular momentum has associated with it a magnetic moment mu in the same direction as the angular momentum L. For instance, the orbital momentum motion of the electron in hydrogen atom also produces, by virtue of this charge, a magnetic moment. With such an atom is placed in a magnetic field beta vector, B vector. The field produces a torque. Magnetic field is represented like this. So mu into B, which then turns to the direction of the magnetic moment vector, and therefore that the vector L is in order to be in alignment with the direction of the field. Now a torque acting on an angular momentum vector is known to have a gyroscopic effect. As a result, the angular momentum vector L presses about the direction of B, keeping a constant angle theta with B all the time. However, if the magnetic field is not uniform, then a net force would act on the atom. It was felt from the beginning that old quantum theory of Bohr and Sommerfeld is in fact a strange mixture of incorporating two diagonally opposite views. While at one hand it invokes quantum mechanical concepts, at the other times it uses the methods of classical mechanics. It is therefore not really a fundamental theory. The domain of the Bohr Sommerfeld quantum rules is limited to periodic or multiply periodic motions and therefore has limited applicability, while the postulates on which the theory is based do provides a basis of understanding the stability of the atoms and the observed features of atomic spectra. The question which remains unanswered is why certain orbits should be completely stable and others not allowed to exist.